Now let's talk about rational functions and trigonometric functions. So a rational function r of x can be written down in this form. So basically r of x is equal to a function p of x divided by another function q of x, right? And both px and qx are polynomial functions. And q of x must not be equal to 0. So these are the conditions. One, that p of x and q of x are polynomial functions, and q of x must not be equal to 0. In that case, it is called a rational function. And the domain of the rational function r of x is the set of all real numbers x. So basically all the numbers in the input set for which the function in the denominator is not equal to 0. So for example, if you had a function, let's say r of x is equal to 2x plus 3 over 4x plus 4, right? So the function in the denominator is 4x plus 4. Now when x is equal to negative 1, that would make the denominator equal to 0. So the domain of this particular example is basically all real numbers except x is equal to negative 1. Okay? So let's see what trigonometric functions are. So we denote and define trigonometric functions as follows. One is the function sine of x, and the graph for sine of x, once you plug in different values of x, is something like this, right? Again, graphical representations make things very easy. The maximum points are at y is equal to 1, and the minimum points, these dips, these valleys, are at y is equal to negative 1, which is why the range of this function is y lies between negative 1 and 1. But the range, the x values, can go on forever. So the domain of the domain is the x value, right? And the range is the y value. So the domain is all real numbers, right? Similarly, we have cosine of x, and it has the same domain and the same range, because the only difference is that instead of starting at 0, this starts at 1. But it's the same as sine of x, right? Now you have y is equal to tangent of x. And once you plug in the values, you find out that the range for this particular function is all real numbers, but the domain is all real numbers except at these points, basically odd multiples of pi by 2, right? So you can just plot this graph, and this somewhat makes sense. Like, this is the graph, right? And it goes something like this. Now at these points, right, these are the points that are multiples of pi by 2, and you can see that the graph is going towards infinity, so it will never touch this point. But again, these points will hence not be in the domain of tangent of x. But as you can see, the y values, they go from infinity to negative infinity, so all real numbers, the range. And another way of basically explaining the tangent function is by breaking it down into sine and cosine functions, right? So you can write down tan of x like this. It's basically tangent of x is equal to the sine of x over the cosine of x. So at any point where cosine of x is equal to 0, this function becomes undefined, so it will not be in the domain. So cosine of x must not be equal to 0. And at all odd multiples of pi by 2, cosine of x is equal to 0. Hence, it is not in the domain. Similarly, you have cotangent of x, which is basically just the reciprocal, so it is 1 over tangent of x. Right, so cotangent of x is equal to 1 over tangent of x, and that will be equal to cosine of x over the sine of x. And as you know, sine of x here must not be equal to 0, and at every single multiple of pi, sine of x is equal to 0. Hence, it is not in the domain of this function. But again, the range is all real numbers. And again, you have secant of x, which is basically secant of x is equal to 1 over cosine of x. And in this case, again, as we did in the case of tangent of x, cosine of x must not be equal to 0. Hence, it will have the same domain and range as the tangent of x, right? So you can see this, and it has the same range as well. And you have cosecant of x, which is the reciprocal, of the sine function. So basically, cosecant of x is equal to 1 over sine x, which means that it will have the same domain and range as the cotangent function, because sine x is in the denominator, right? So hence you have all real numbers except for the multiples of pi, right? But you have a difference in the range as well. Once you plot the graph of cosecant of x, you'll understand that the range is this. The absolute value of y must be greater than 1, right? So that's what this is. Now we need to discuss inverse trigonometric functions and exponential functions. Again, once you plot the graphs, you'll understand. But in simple terms, when y is equal to sine inverse of x, you take sine to the left-hand side, and then it will take the sine inverse function to the other side, and it will become a sine function. So in this case, x will be equal to sine y. And once you plot the graph for this particular case, you'll find out that this is the range and this is the domain. And you have same rules for every single inverse trigonometric function. And once you plot the graphs, you'll find out the limitations in the range and the domains, right? But the simple rule of thumb is that when the inverse function is on the right-hand side, you take it to the left-hand side to make it into a normal function, a trigonometric function, basically. Now let's discuss exponential functions, a function in which the variable basically x appears as the exponent is called an exponential function. Sorry, I have a bit of a cough. Now, here's an example. You have e to the power a of x. Now you see this x over here, it's in the exponent, right? And similarly here, x is in the exponent. In this case as well, x is in the exponent. In this case as well, x is in the exponent, right? So these are all exponential functions of x. Fairly simple.